Sorry for getting this one out kind of late this week. It's been a little crazy this week. But this says week 5, but for you it will say, I think when I save it, like something along the lines of functions and t-tests or something like that. It'll be in Canvas, which you would know because if you're here watching this video, you already found it. Yeah, so here are the packages that we're going to be using in this video. We're going to want to import our most recent data set, whatever your name and number is in an Excel version. You'll want to change that to whatever you've got yours named, and import the data set. You should be somewhere around this. You may be, a few more or a few less, depending on if I mistakenly created some weird odd variables at some point, or you did. We're gonna start with learning functions. So in this upcoming homework 4, you're gonna have to bring in a whole bunch of feeling thermometers to your data set, 47 to be exact. And even if you're copying and pasting the code over and over, that's pretty time consuming to have to do that 47 times. Since these can all be recoded with the same code, every feeling thermometer on the ANES is coded the same way. We can actually recode these all in just a few steps. So far we've been using functions already quite a bit, but we haven't made any of our own. But all functions work essentially the same. Here's the structure. It's going to have a name, so some name for the function. And then to create it, you type function and in parentheses X, and then a curly bracket, and then some lines of code in between the closing curly bracket. And what happens then is in your code, you substitute the variable name with an X, which is this here. So this saves all these lines of code as an object over here in your environment for you to call back up later. So now, once you run this, you can just say my function and then enter in some variable name. And then R will run all of the code that's inside that function that you saved in there with just that one simple command, because you've already assigned everything in those curly brackets on whatever you designate X to be. So if we look at some of the functions we've used so far, we can see that some of them are really short. So some of you may not be able to run this, but you can just see what I've got. So like this is what happens behind the scenes when you run the disttab function. It runs these few lines of code here. But then some functions can be super long and complicated. So if you run this, you can see that the underlying code for the cross table function is super long. It's all of this, all the way. Here we go, all the way up to here. So like all of this code that happens after this is stored in this one little word, this function here. Essentially, packages work that same way. They just basically package all of this code and this function into something that you can call back up, that you don't have to create every time you start a new session of R. Okay, so we want to create a function with the code that we would be using to recode the similar variables. For this example, we're going to use the candidate trait variables. And then you can apply this concept to the feeling thermometers later when you do your homework. So in these variables, the respondents are asked how well these particular traits, describe each presidential candidate. They're all coded from 1, which is extremely well, to 5, which is not well at all, as well as the usual -9, -8 values that represent refused and don't know. We can look over here. I think I have it pulled up. So like this one is, in your opinion, does the phrase "he provides strong leadership" describe Joe Biden extremely well, very well, moderately well, slightly well, or not at all well? And think of these not as the liberal to conservative continuum that we did with the policy variables, but just as a little or a lot. So I actually in this code flip this code because it doesn't make sense to me. Like if you're trying to say that this describes Joe Biden very well, it doesn't make sense to me that the value would be small or a 1. It makes more sense to me that the value would be 5, because 5 is bigger than or more than or, better than 1. So I actually in the code over here flip these. So the code that we would just, if we were going to do every single one of these by hand, here's the code that we would use to do that. So, my data for our data frame, and then give it some trait, some name, and then we'd use the if-else function to flip the values and then assign anything other than 1 through 5 to be NA. To actually create the function, we just substitute X for the variable names. So we're going to give our function a name. So it's recode trait function. And then type the word function, and then the X in parentheses, and then open up the curly brackets. And then here's our code, which you could just copy and paste from up here. Or, if you, I have to think this through when I'm creating a function, and I have to type I have to do this for 1, just so I can see it. And then I can figure out what I need to change to X and how I can get it to fit in here. So if you change, substitute X here, substitute X here, this is what you come up with. So if you run this, you see that here's the function over here. It showed up in your environment. And so that's step 1. So now we just need to know what we're going to run this function on in order to create all these new variables. So for this, we're going to use the function lapply, which applies a function over a vector or a list. So 8 variables, I would not create a function for 8 variables. I would for 47, but just as an example, we'll do it on these 8. So these 8 variables don't exactly exist in a single vector in our data set, but they should in your code book, or they will. So since you're going to recode these 8 variables, you'd want to go and look up what each of the 8 are and create variable names for them. And what I did was I put through this just mini trait code book together, where I've got a list of the ANES variables here and a list of the new variable names that I want to give it here, with nice little R-friendly column names: ANES variable, my variable. And then this is on Canvas. Hopefully you already saw it and downloaded it. If you didn't, you're going to want to do that before you can run the rest of this code. So if you've been keeping a code book in Excel, this is going to be handy. You should be able to just go and pull. I don't know if, you've gone out and looked up all of the variables in your data set yet and put them in the code book. You're certainly not required to, but if you've already done that legwork, It's going to be helpful. But probably step one for the homework is going to be to copy and paste all of the variables for the feeling thermometers that you're going to recode into your code book, and then go and look up the what each of them mean and assign them a name. And then that way you can just take those two columns, slap them into a separate, you don't want to use your full code book to do this, because then you've got all that extra stuff in there, and then you have to figure out how you're going to extract these two particular vectors. So I would, while it's a good idea, while you should have all of these in your main code book, you probably want to create a little mini code book, like that's set up like this, specifically for those feeling thermometer variables. Once you have that saved in your working directory, then you can just import the mini code book with an import function. And you see that if you do that, you'll have 8 observations of 2 variables. For this, when you do your feeling thermometer mini code book, it should be 47 observations of 2 variables. And you can, take a look at it. You can see it looks just like it did in the Excel spreadsheet with your variable names and the ANES variable names. So now that we've got that vector sitting out there somewhere where we can grab it, or those 2 vectors, we can use the lapply function to apply our recode trait function to the vector my code book ANES variable. And then by assigning the resulting values to a variable name, then we have that we've created and recoded 8 variables, like all at once, or 47 when you apply this to this concept to your assignment, or in essentially 5 lines of code. So if you remember that using the square brackets, we can get or extract parts of the various data structures in R, then what the code looks like to do this is going to look like this down here. So I know that there's a lot going on here that you're probably not understanding what's happening. So basically what we're looking at here is on the right, we're extracting the vector my code book ANES variable, which this is what, like this comma here, so we're telling it to get all of the rows because there's nothing before it. So and then we want just the column my code book ANES variable. And we're going to concatenate that with my data, so it knows to smush those 2 things together and then put the $ operator in it when it's all done. And we're going to do that for each unit in the vector, is essentially what the lapply is telling it. We're going to run this function, recode trait function, over each unit in this vector. And then we're going to, on the left over here, we're going to name each result of this application of the function, of this function, what we're telling it over here, which is similar to what's going on over here. It's except for this time we're telling it to grab the my variable vector so it knows what to name it, and we're concatenating that with my data. Okay, so hopefully you followed that. If not, trust me, it runs. So if you run that, you'll notice that we've now added 8 variables to our data set. I went from 198 to 206. You went from whatever you started with plus 8. So we know that it created these variables, but we'll want to spot check. So just run a couple of tables on the original variable and the new variable that you created. With 8 of them, you're pretty safe in assuming that probably if you didn't get an error when you ran the code, and if these 2 match, which they do, 407, it just flipped them. Remember, the -9s are now gone. 5 matches 1, 4 matches 2, 3 matches 3, 4 matches 2, 5 matches 1. You can be reasonably certain that it probably worked. When you run this on your feeling thermometer variables, it wouldn't probably hurt to check, maybe 2 or 3 to make sure that they're the same. But again, if you're not getting an error and a couple of them are correct, then you can be reasonably certain that they're all correct. So this is just another example of using function as a shortcut. You're not going to need to do this on your homework. This is just something else that I'm showing you, but just another example of a function. So I've named this function freq function. And again, here's the format for creating a function. So it's function, x in parentheses, open curly brackets, with this code, which is just the distab function that we've been using to create frequency tables so far, and then a close curly bracket. If you've not been able to get this to run or you've had problems with it, don't worry about running this. Again, I'm not going to make you do it on the homework, but just so you can see like another example of this. So you see it created the freq function over here for me. And then you can actually do this without, you don't have to create an Excel document every time. The Excel document in this scenario was just to provide a way to easily assemble the vectors that you needed to make that function work. In this case, we can actually tap in to the data set to get the vector that we want. And so if you look in like run names on the data set, you can see all the names of all the variables that we've created so far. And you can see that the ones that we want to run the frequency table on, if we're going to just run it on the ones that we just created just now, let me see, is it really, I probably need to fix this because this is last year's code. So I've actually got, this one is 197, 198. So I actually want to go 199 to 206. So this is saying to assign to this value my variables, the names of the variables in my data from variable 199 to variable 206. And so now we've created this vector here with all of those in it. And then we can run the frequency function on this little, we'll smush together my data with my variables. And it will just quickly create all of those frequency tables like we've been creating in with the distab function. Okay, so next we're going to move on to t-tests and anovas, which you have not a clue what I'm talking about if you're watching this before class on Tuesday. Or maybe you do if you've been exposed to them in some other classes. We're going to start off creating a dichotomous variable for party ID. So if you run a table on your party ID 3 variable, just to see what's in there, and then this code here is going to just basically set the independence to NA. So we've only got the Republicans and the Democrats in this variable. And that, you see these match up, Republican 3, Democrat 417. And then we will...
I didn't get that. Could you try again?
Wait, Siri, I don't know how that happened. Excuse me. Anyhow, so the function to perform a t-test is pretty intuitive. You can run this here to look at the documentation and kind of see like how the structure for the t-test looks. There's actually a few different ways that it can be set up, and it can how you set it up depends on what you're trying to look at. So it can be used to compare the means of two different variables, or compare the means of two different groups within a variable. So like men and women in gender. Yeah, I think that's it. So to compare the means of two different variables, The structure is going to look like this: t-test, and then in the parentheses, you're going to have x, comma, y, comma, and then alternative equals, and then you'll choose one of these. There's 3 different options here. So where x and y are going to be the 2 variables that we're comparing, and the alternative argument indicates whether we're doing a 2-sided test, a 1-sided test where x is greater than y, or a 1-sided test where x is less than y. So if our hypothesis is that Biden is rated as more honest than Trump, then we are going to want a 1-sided t-test where the alternative is greater. So if we run that, we get some output down here. It gives you the t-value, it gives you the degrees of freedom, and it gives you the p-value. So this 2.2 to the negative 16th is like super small number. So this is significant. It'll also show you the means where x is, so how many people think Biden is honest and how many people think Trump is honest. So we see this is greater than, x is greater than y. This is the same thing as if we switched x and y around and instead put alternative equals less, we're going to get the same results down here. It's just going to be, that's, the signs are going to be flipped in this instance because we've flipped x and y, but the interpretation is the same. Now that would be different if had you left the x and y the same but changed alternative to less, so where you had Biden here and Trump here, that's a different thing. We can do that really quick, I guess. So in this case, so your p-value is 1, so not at all significant. I'm gonna put this back to so it looks right when you guys see it. Or if your hypothesis is just that they're significantly different and you don't really care which one is more, which one is less, you can just leave that alternative argument off because 2-sided is actually the default. So if you run that, then you get, you still get a t of negative 10.635. You get the degrees of freedom. You get the p-value that is highly significant. And you get the means, but your interpretation is like, it's different from these up here. No matter what, these numbers all stay the same, but how you interpret it is ultimately just different. Oh, okay. I did this here. So this is kind of what I was getting at when I changed it above. Like, it's not significant because what you're at, the numbers are all the same, but it's not significant here because you're asking it something different. So you're asking it is if it's which side of the curve, you're talking about which side of the curve you're falling under. Okay, so we can also use the t-test function to compare the means of some outcome variable for the categories within a dichotomous variable. And I'm gonna, so that's why I did that. That's why I had us create this just two-party ID, just Republican and Democrat. So here we use a formula instead of just this structure up here. rather than, and the formula takes the form or the structure of the dependent variable, and then this little tilde, and then the independent variable. This time we're only using the variable names, not, so you see this just says Biden strong, and it doesn't say my data with the $sign in Biden strong. That's because we add this data equals my argument, which tells it which data frame to look in, or which data set to look in. So we've run that, and so it even kind of tells you what your hypothesis is, or what your alternative hypothesis is. True difference in means between group Democrat and group Republican is not equal to 0, is what your alternative hypothesis is. And because your t-value is so high and your p-value is so low, this difference in means between Republicans and Democrats is significantly different from 0. The next test that we are doing this week is an ANOVA. And so the difference, Rick will get into it, but basically the difference in I think the difference in these two is the DV has to be categorical. No, DV has to be maybe it doesn't matter. I don't remember. Rick will tell us what the difference between when you run an ANOVA and a t-test. I feel like it matters. I think maybe they all have to have an interval level outcome. Anyways, we can look at the documentation for the ANOVA. It's just this AOV, and then in parentheses is the function. This one is going to take the form of a formula also, similar to the t-test. When we do regressions, it's going to look the same, so it's really going to get easier to learn as we go, because the formulas essentially just kind of build off of each other. They look the same in structure, and they'll build off of each other. So here we're actually going to, rather than just running it like we did up here with the t-test, we're going to actually assign it to we're going to give it a name. We're going to name it just M1 for Model 1. But it's going to look really a lot the same as what we did up here, where we have the dependent variable and the tilde, and then our independent variable. And then we're going to tell it which data set to look at. So if we run that, we see this model shows up over here in our environment. And if you look, there's a bunch of crap in there, and you're probably like, what the hell is all that? It doesn't matter. We'll do some stuff later on where we'll be working with these residuals. And probably the coefficients too. We'll need to extract those. But for now, just know that we've created this model, and we want a summary of it. That'll give us most of what we want. So what this is telling us is that race is significant. The categories in here are significantly different from each other, but it'll tell us, it's only telling us that this model is significant. It won't tell us which groups are different from each other within the race variable. For that, we need to run what's called a post hoc test. And there are several that we can run, and Rick will explain the difference between those on Tuesday. The first one is Tukey, a Tukey test, and that is found in base R, so you don't need any additional packages for that. And it's just this Tukey HSD with the model number. or the name of the model in the parentheses. If you run that, it'll actually give you a bunch of stuff. It will give you, for every comparison, every group comparison within the race category, it's going to give you what the difference is, what the lower, but the lower bound of the confidence interval and the upper bound, and then it's going to give you a p-value. So we can see that every combination here is significant except for other race and Hispanic. So Hispanics and blacks are different from each other. Other race and black, white and Hispanic, white and other race. All of those comparisons are significantly different from each other, but other race and Hispanic are not. What this does not give you is the means for each of the particular categories within that group, which is something I believe we ask you on the homework. So here is the code for that. You're just asking it for the mean of this variable when just in the observations where race is white. And then, of course, you need this na.rm equals true argument. Otherwise, you're going to get just an error. And so the mean for thinking that for how strong of a candidate, I guess, whites think Trump is this 2.71. There's a couple of additional post hoc tests that Rick will talk about. One is called the SNK, and one is called the Sheffy. I think it's Sheffy, not Sheffy. I don't remember. But they're found in this package Agricole. So you'll want to run this to install it if you haven't installed it previously, and then you'll want to open the library to be able to access those things. These have this little, so this is how the format is set up. It's a little bit, it's not just the model number like this is up here. You have to also feed it the variable that you're dealing with and add this console equals true argument. I think this is just so it'll actually display the results of the test in the console. So the output for this is there's a kind of a lot. So this actually does give you the means for each of the categories, and the standard deviation, standard error, these are all things that Rick will talk about, and then the min and the max, and a bunch of information here. What you're really looking for is this here. It gives you these letters for each of the categories, and if any categories with the same letter are not significantly different from each other, which is what we already found in the other tests, if you remember. Other race and Hispanic are not significantly different from each other. All the other combinations are. And then the Sheffy test is also kind of run similar to, this was just me trying to remember how this worked because I had the wrong variable in there. Similar to the SNK test. I feel like it does give you it also gives you all this extra information. Yeah, no. Yeah. The means, the standard deviation, all this crap. And then you'll notice that this actually is different from up here. The SNK test and the Tukey test both were the same. The only combinations that wasn't significantly different from each other was other race and Hispanic. This one is actually telling us that in addition to that white and other race are also not significantly different from each other, which I feel like that's kind of a load of crock, but that just kind of goes to show you like there's it's important to be running the appropriate tests, which Rick will explain to you how to do. Okay, and then two-way anovas is going to be where you're looking at more than one predictor. So instead of just the race variable as a predictor, we're also going to use the sex variable as a predictor. I've named this one Model 2. It's the same structure as a basic ANOVA. You just, in addition to the dependent variable and the tilde and an independent variable, now we're just going to add another independent variable. So now we've, why didn't that run? Oh, because I missed the close parenthesis. There we go. Now we've got Model 2 over here in addition to Model 1, and if we run this summary on it, we'll see that while race is significant as it was in the other model, the sex variable is not. And I don't know why that threw an error. But the Cheffe test worked. This gives you, again, all the means for everything, every combination. So, black and male, black and female, Hispanic and male, Hispanic and female, other race and female, other race and, or other race and male, other race and female, white and male, and white and female, and the mean for each. And then again, means with the same letter are not significantly different from each other. So that is all of the computational stuff. And Rick will cover the what all this means part on Tuesday.